Hey, everybody. Let me put my chat up. Okay, I'm going to share my screen. Okay. Still so much going on. Oop. I hope everybody's doing good. Even though we're not in the classroom. Okay. Let's see. I'm going to start. Let's see if I can minimize some of this stuff. And we can start our attendance. Okay. And we still got a few minutes before class starts. All right, we got a bunch of people on. All right. 39 so far. My handheld clicker does not work from home. No, it does not. But the good news is that today I am not going to be doing iClicker for points, because if some people are evacuating, you know, things are going on. I'm not going to do that today because kind of not fair. So Lillian, would you send me an email that says, Dr. B, I was in class, and I'll fix your attendance. So do we pick present in classroom if we're in Zoom? Oh, everybody's going to be on Zoom. It doesn't matter. Everybody's on Zoom. So everybody picks B. You're remote at home. But Lillian, I can go in and manually change yours. Okay. Let's see. Minimize that. So yes, if you have a handheld clicker and you are unable to put me in class, unable to check in, then you need to send me an email so I can fix your attendance so you get credit for being here today. I joined, so I'm not sure. You have a handheld. Okay, if you are unable to do iClicker attendance like you normally do because you are in class, what you can do with the iClicker is just send me an email, make a comment in the group chat so I can see that you're here, and then send me an email that says, I checked in on the Zoom chat. Can you please fix my attendance? And I'll go ahead and get that fixed for y'all. I'll say that one more time once class officially starts at noon. Okay. A few minutes to wait for everybody. At least y'all aren't in the cold, cold classroom. That's a perk. You don't have to be frozen. Yeah, be careful what you wish for in a warm house with a hurricane coming, because I really like my air conditioning. So we got to balance that, right? Please do joke of the day. I'm going to do joke of the day. At noon, I'm going to do joke of the day. It's kind of like not really a joke, but it's a joke. I thought it was funny. I promise I'm going to do joke of the day. I thought y'all didn't like my jokes. I thought my jokes were too cheesy. Giving everybody about another minute to get online. Let's see, how many people do we have? Ooh, 66. We're doing good. Oh, good. I'm glad they make you smile. Good. Yeah, I think it's nice to start. It starts with something fun. So what I have today is biology related. I'm glad they make your day. Yay. All right. Well, I'm going to keep doing them then. Knowing how much I'll like them, I will definitely keep doing them. And I'm on a swivel chair, so I'm going to have to work really hard not to swivel, because I know that's going to look really strange. All right, let's see. Okay, so we are at We are at noon, so we can go ahead and start. So I'm starting with our joke. So y'all know the mitochondria, right? The powerhouse of the cell. Okay, so in October, right, the mitochondria turns into the phytochondria and becomes the haunted house of the cell. It's not really a knock joke or, you know, traditional joke, but I thought it was really cute. So the mitochondria turns into the phytochondria and becomes the haunted house of the cell instead of the powerhouse of the cell. Yeah, us nerds, we like those. We like our nerdy jokes. I love it. All right, so virtually laughing. Oh, you saw that on Facebook? We're laughing in spirit. That's good. Okay, so check in on iClicker attendance if you can. If you are unable to click in on iClicker, like you have a handheld or something like that, and you can't do it, so what I want you to do is send me an email, like make a comment in Zoom chat that says, hey, Dr. B, I'm here, so I can verify that you were here, and then send me an email that says, Dr. B, I checked in. I have a handheld remote, so I couldn't check in. But I checked in on the Zoom chat, and I will go in and I will manually fix your attendance so that you get credit for being here. Yay. So just check in on the chat if you have a handheld and you can't do it. I understand. I know how it goes. I'm proud of y'all for all being here with all the craziness going on. And then just don't forget to send me that email, because that's how I'll check you off. Okay, so what we're going to do today is we are not going to do clicker questions because people with handheld clickers can't do them, people who are evacuating, things like that. So I'm not going to do points today because I feel like that would be unfair to people. So we're going to do our in-class problems, and you remember the little thing I told you that you're going to have for this class right here. So right here, these chapter 6 activities, there are 2 of them. One is glycosidic bonds and one is reducing sugars. We will need these after we're finished with the ICP, because we only have a little bit, the ICP, the in-class problems, we only have a little bit of that left. Okay, so I can minimize this, and here we go. Oh, that's not what I wanted to do, darn it. See if we can get this right. Okay, so we're going to our ICP, and I want my chat. It went away. I can't see my chat. I'm gonna have to resize this because I really want to see everybody's face. And oh, I bet I know how to do it. Let me do a different share with y'all, and I think I'm gonna be able to do this a little bit differently. Hang on. Y'all are so patient and so sweet. Okay, now I can see the chat, even though y'all might not be able to, but you can change it on yours. Maybe if I could make this a little bit bigger for us. Nope. Y'all are so patient and so sweet. Okay. All right, so we're talking polysaccharides. You do not have to have your camera on. As long as you're here and you're paying attention, we are golden. So we're talking polysaccharides. So as much as y'all can respond in the chat, that would be really awesome. But I know this is really weird. So polysaccharides, how do we know something is a polysaccharide? What does poly refer to? Many, more than how many? More than 10, good, more than 10. So what we want to do is we want to go over our differences between polysaccharides. And this section was really short, so I just went ahead and left the whole in-class problems for us to do in class, even though we're not technically in class. So amylose and amylopectin. So when we talk about these, both amylose and amylopectin, so we'll do A first, so A. So we want to tell how they are similar and how they are different. So I'm going to start with how they're similar. So both of them are, of course, what section are we in? Polysaccharides. Okay, they're both polysaccharides. And they're inside of plants, so found in plants, and plants use them for storage. So used for storage. Ooh. Right? And you got to remember why plants need storage. Plants need storage because it does not shine 24/7, and so they need to be able to store food for when the sun goes down, for at night. And so this is where plants store their energy in polysaccharides. So if we look a little bit more detailed into their structure, they all have a similar bond. Anybody know what bond that is? They both have the same glycosidic bond. Anybody know what that is? Alpha 1, not alpha 1, 6, alpha 1, 4. Alpha 1, 4. And so alpha, ooh, that's the symbol, alpha 1, 4. Okay, good. All right, now how are they different? Anybody know? How are they different? So amylopectin, yes, amylopectin, M-Y-L-O-P-E-C, pectin. Now they do have an additional bond. The glycosidic bond that makes that main chain is an alpha 1, 4. But in amylopectin, you actually have branches that will come off the main chain. Amylopectin has branches that are alpha 1, 6. So their branches are alpha 1, 6. Does amylose have a branch? Amylose is unbranched. So it has no branches. It is a straight chain. Right. Okay. So we see how they are very similar. They're both used in storage, but they're slightly different. So amylose is like the basic of what it is, and then amylopectin is branching. And so we call it something slightly different because it has those branches. Okay. All right. Oh, you know, I'm taking up tons of room here. Tons of room. All right. Let's try a different color. B, amylopectin and glycogen. Oh, now you have to remember we said amylopectin was in plants for storage. So let's start with different. How are they different? Well, we know amylopectin is in plants. How about glycogen? Animals. Good, animals. So they're both used for storage. Both, they are storage, S-T-O-R-A-G, storage polysaccharides. But different organisms store them, right? Now, we knew that amylopectin has branches, right? Amylopectin has branches at alpha 1, 6. How about glycogen? Does glycogen have the same? They both, very good. They both have branches with alpha 1, 6 linkages. That's true. But what's different about those branches? They're not quite the same. No, they're composed of the same thing, and they have the same branching glycosidic bond, but they branch more often or less often. So in amylopectin, you're going to branch every 25 glucose units. So for every 25, you're going to branch. In glycogen, you're going to branch a little bit more often, and you're going to branch every 12 glucose units. So does everybody see my screen? We're all okay on, because I haven't done this kind of a thing before live. Okay, good. If I do something wrong, if you can't see something, please tell me right away. Good. Thank y'all for responding. That's so awesome. Okay. So we kind of have our ideas about storage, and then storage in terms of plant versus animal. So now let's look at some of our other ones. Let's look at amylose and cellulose. So if we're comparing these, right? Well, they're in the same category. So they're both polysaccharides. That's kind of like your given answer. They must be polysaccharides. Okay. So they're both polysaccharides. Where are they found? Amylose and cellulose. Those are in plants, polysaccharides in plants. That's right. Okay. They both have D-glucose as units, right? They're polysaccharides, so they're multiple units of the same thing over and over and over again. So what is that unit that gets repeated? And that's D-glucose. But they're not the same. Can anybody give me a difference between amylose and cellulose? Versus cellulose. Cellulose is structure. Very good. Cellulose is this is designed, it's functions in structure. Amylose, what we just talked about, functions in storage, right? So that's storage for energy needs. So they have different functions depending on their structure. So if they have different functions, they have to have different structure. So how are their structures different? So cellulose is beta, very good. Cellulose is beta 1,4, and then amylose is alpha 1,4, and those are our glycosidic bonds. So either you're an alpha 1,4 or a beta 1,4. So cellulose, just because of those differences in glycosidic bonds, whether it's cis or trans, is going to make a huge difference in how those strands of the cellulose lay. They lay like one on top of the other, and they can pack in really, really, really tightly. And so cellulose ends up being really great for structure because they lay so parallel and so tightly packed that they can then help the plant have support and things like that. So that's really a cool way that structure drives function, which is always fun in biology. I love that concept. Okay, B, cellulose and chitin, however you want to say it. So both of them are for what? What function do they have? Both function in structure. Both function in structure, right? But not quite for the same organism, right? So, what are we doing? Cellulose versus chitin, right? So we said cellulose were plants. How about chitin? Is chitin in plants? In insects, in crustaceans. So in hard shells of different organisms, right? So how are they structurally different? They both function in structure, but we know that insects have a much tougher exoskeleton than plants do. So what makes them unique? What makes that chitin unique? Anybody know? We know in cellulose we have D-glucose units. Do we have those same D-glucose units in chitin? You know, it's a really big word, right? It's a really big word. It's the N-acetyl, C-T-Y, acetyl Glucosamine, C-O-U-C-O-S-I-M-I-N-E, glucosamine, N-acetylglucosamine. Big old word, right? So what that means is basically you start with a normal glucose structure. I'm going to draw it where I have kind of room up here. So if you have a normal glucose structure, we have our oxygen inside of our ring, and we have our normal CH2OH, right? And we have some hydroxyls over here. And we have a glycosidic bond to another one, right? That's another, this is going to be another ring. And I'm not going to draw all the details on that ring. But what we know is this bond right here, instead of having a simple hydroxyl on it, we're going to have some extra stuff. So what's going to be that extra stuff? In acetylglucosamine, we're going to have an amide group, so a nitrogen, right? So it's an NH on that one. And then that nitrogen is going to be bonded to, what is a C double bonded to an O? What do we call that? A carbonyl group. A carbonyl group. And then if we add a CH3 to that, what we call this an acetyl group. E-A-C-E-T-Y, an acetyl group. So this is an amide, and that's an acetyl group. And so this is why we call it N-acetyl glucose. That's part of the, it started out as glucose, and then amine instead of amide, but it's the same thing. So that's where the name comes from, but it's a modification of glucose. It's very similar, but it's got that extra modification, and that gives it a lot of strength, Okay, so give the name of one or more polysaccharides that matches each of the following descriptions. Not digestible by humans. So a lot of times when you eat, there are certain plants that you eat that are really high in this one particular polysaccharide, like, oh, we were talking about it in class the other day. Oh my goodness. Like a stalk. I can't believe I'm blanking on celery. Thank you. Celery. It finally got here, right? Celery is really high in cellulose, right? So that one's not digestible. What's another one that's not digestible by humans? Yeah, I can't spell any day. Don't worry about it. I can't ever spell. Anybody else? What's another one that's for strength, right? Those are the ones we can't digest. That is our, well, cellulose is one of them. The other one is chitin. So we can't eat cellulose and we can't eat chitin. Well, we can eat it, but it doesn't digest. We don't break it down. The storage form for carbohydrates in plants. So what do we store? What do plants store? Plants store it as, hop in anytime. There are two that make up starch. So we call it starch. But yes, amylose, A-M-Y-L, amylose, and amylopectin. So it's the two of them, and the other one too. Yep. It's one of those days, right? All right, contains only alpha-1,4 glycosidic bonds. So this is one of those, it has to be a straight chain. What only contains alpha-1,4 glycosidic bonds? There's only one, amylose. Good. Okay, glucose polysaccharide with the most branching. So with the most branching, it's going to have the most branching at the lowest number, right? We had two that branched. Which two branch? Glycogen was one of them. What's our other branching? Amylopectin, right? Glycogen branches every what? 12. Amylopectin branches every 25. So which one has the most branching? The one that branches the most often. That would be glycogen. Okay. And y'all can stop me anytime. It's hard when I can't see anybody's faces. If you have a question, stop me. All right, give the name of one or more polysaccharides that matches each of the following definitions. The storage form for carbohydrates in animals. So your key there is animals. This one is glycogen. And that's one of the reasons why it's really easy for us to get stored sugars into our bloodstream, because glycogen branches so often that we can really, really easily break it down and get those individual glucose units that we need in the bloodstream. Okay, contain only beta-1,4 glycosidic bonds. Remember that beta makes it a little bit stronger. So these are going to be the ones that we can't digest, and that would be cellulose, C-E-L. See, I can't spell today. Cellulose and chitin. Okay. Contains alpha-1,4 and alpha-1,6 glycosidic bonds. Both alpha-1,4 and alpha-1,6. Amylopectin, yes. Anybody got another one? Glycogen. Glycogen, good. Yeah, it kind of is. It kind of is. Unfortunately, something you need to memorize. Sorry, Jake. All right, let's see. Produces maltose during digestion. So as you're digesting it, you know that there are certain ones that we can't digest. We can't digest cellulose. We can't digest chitin. So it really narrows down your answer choices here. So which ones can we digest? And then within that category, it's amylose. Oh, I really can't spell today. And glycogen. Thank y'all for catching everybody on the chat. I appreciate that. Okay. All right. Now, this is cool. I really, 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 really like this section. I think this is really interesting and really gives y'all an explanation as to why carbohydrates are important in blood typing, in the immune system, and all kinds of stuff, right? So if we remember our different people who were type O, we had type O, type A, and we had type B. Do you remember what was in those people who were type O, A, and B? Anybody remember that? I think I have a bunch of room up here. I think I can move that up here. Anybody remember? So if you go back, it was something with the chain. It was. So watch, I'm going to pull up our PowerPoint. I know the screen went white, but where did I put that? Where's my lecture 6? There it goes. Okay, so here we go. No, disaccharides were over here. We want polysaccharides. So here we go. So remember this? I can cut and paste this. Remember this when we talked about it from lecture? What's different between the different types? So I'm going to go and put this on what we were working on. So we're right here. Okay. So if you're type O, if I can kind of just zoom in on that. If you're type O, you have three different kinds of glucose molecules. You have an N-acetylglucosamine, what we talked about before. You have a galactose, and you have a fructose. So depending on what blood type you have, it's just an addition onto this. So this is like the surface of the red blood cell, and hanging out on the outside surface is this chain of sugar molecules. And so if you're type O, you have three different things on the chain. If you're type A, you have these same three, and then we're going to add one more that's a little bit different, right? So it makes your chain look different so that your body can recognize your immune system can differentiate, okay, this is Dr. B's cells versus this is somebody else's cells. This is foreign, right? Type B, it's the same way. We have the same 3 here that are in type O, except now we have a galactose as an extra. Okay, so that's really, really important for you to kind of remember when you're answering these blood type questions. So, explain whether the following blood types could be donated to a person with type B blood. So in A, we want to take A blood, type A blood, and we want to give it to someone who is type B blood. What do we think? We think that's a good idea or a bad idea? I think Amaya's right. I think Amaya's right. That would be a very bad idea. You might actually kill somebody that way. So we want to make sure we get this right. Okay, so our type A blood, if we go up here and we look, our type A blood has an N-acetylglucosamine group. Our type B blood has a galactose group. So if I give somebody type A blood who has type B blood, their immune system is going to see that new blood and it's going to attack it, and it's going to make their blood coagulate, clot, and they could die from that. So you absolutely do not want that to happen, right? And why can't you do that? Because who can type A donate to? Let's talk about that. Type A can donate to who? They can donate to someone who's A, and they can donate to somebody who's AB. Because what is AB? AB is that you have a red blood cell, and that red blood cell has both, like if that's your red blood cell, it has both the type A sugar and it has the type B sugar. So you can receive anything that looks like you or is less than you, but that's it. So type A can donate to only type A or type AB. That's right. A type B person can, let's talk about this, receive, C-I-E, receive from who? Who can type B receive from? It can receive from themselves, which is a type B, or less than them. So if you looked at here, here's type B, here's type B. What is less than type B? Well, that's only type O. Do you still upload these lectures? Yeah, I did. Ariana, did you not see the lectures? The lectures are you talking about the Zoom that we're doing right now, or the lectures? Yes, I'm recording and I'm gonna post this one. Absolutely. Absolutely. Yes, I'm going to post. Absolutely. Okay, so type B can receive from B and can receive from O, right? Anybody can receive from O. Have you heard on whatever medical show you're watching, you know, somebody comes into the ER and they're like, hang a bag of O-neg and type and cross, right? You've heard that? Well, what are they hanging? They're hanging a blood bag that is O negative. And so we don't really talk about the RH group in this class, but you will later in another class in a biology. But they're hanging O, type O blood, because anybody can receive O, because O is like the minimum, right? Every other blood type is type O with something added onto it. So anyone can receive type O blood. They are the universal, type O is the universal donor. O is universal donor, right? And then AB is the universal recipient. So the universal recipient means that they can receive blood from anybody. They can receive from A, they can receive from B, they can receive from O. They can receive from AB. They can receive from anyone because they have the maximum number of stuff on the outside of their cells. So they can get it from anyone. Okay. So A, we said this was no, don't do it. Right? How about B? So could we take AB blood and donate it to a person with type B blood? That is, again, a resounding no. Please don't do it. Please don't do it, right? Okay. Let's try another one. Explain whether the following blood types could be donated to a person with type O blood. So can we go from somebody who's B and donate it to somebody who's O? This is another big, big no, right? How about AB? Can we go from AB to O? No. Now, here's the stickler. You're right, Erin, you're right. Type O blood can only receive type O blood. So they're the universal donor, but they can only receive O blood, right? Because if they're that simple chain that had only 3 sugars on it, they can't get anything other than that because their body would see it and wouldn't recognize it. It would be marked as foreign, and then their blood would clot. It does suck. It does suck. But if you are a type O person, please, please go and donate blood. Please, from the bottom of my heart, please go and donate blood. Yes, they call you every week to donate. I'm sure they do. I'm sure they do. It would be awesome because when people come in injured, right, we don't know what their blood types are. And so in order for, is type O common? It is, it's not as uncommon as you think it is. Yes, you can donate if you're O positive. You can absolutely donate if you're O positive. You can only give, if you're O positive, you can give to somebody who is A positive, B positive, AB positive. But O negative is the rarest. O positive is pretty common, but O negative is rare. So if you're O positive, you can donate to all the positives. If you're O negative, you can donate to all the positives and all the negatives. So you can donate to everyone. So, but everybody should go and donate blood. It's a really good thing to do. It's a really, really good thing to do. Okay. So the other reason why sugars are really important, right, is we use a type of sugar to prevent blood clotting. Your blood clotted. Oh, well, then don't do that again. Stay safe. That's important. Because you donate blood for extra credit. I don't do that because some people can't, and so it's not fair. I wish I could, but you get brownie points. But you know, I can't even make brownies right now for everybody. All right, so how is the polysaccharide heparin different from the glucose polysaccharides? So we give heparin to people who might run the risk of having a blood clot, right? And so heparin is an example of something that is an anticoagulant. Have y'all heard of that before? Anticoagulant. Have y'all heard that before? Anticoagulant? I bet you've heard of another anticoagulant, but it wasn't called that. I bet you've heard of aspirin. And we say aspirin is a blood thinner. Have you heard that? You notice my air quotes. It will not thin your blood. That's a lie. It is technically an anticoagulant. So it prevents blood clots from forming. And so that's exactly the same thing that heparin does. Heparin does it kind of at a much more extreme level than aspirin. But you know, a lot of people who have heart issues, their doctor will prescribe a low dose aspirin. And so it's not that it's going to prevent clogged arteries from forming, but it will prevent clots from forming on those clogged arteries. And so that's why they prescribe a low dose aspirin kind of daily. Okay, but we kind of skipped, like I went ahead, I apologize. So how's heparin different than normal glucose, right? So normal, if you have a normal glucose polysaccharide, so if you are the glucose polysaccharide, What are your units? What do you think? You have units of what? Glucose. I can't even spell glucose, but you have units of D-glucose because you're a glucose polysaccharide. So how about heparin? Does heparin have units of D-glucose? No, it has 2 monosaccharides as a repeating unit. Right? So one's an oxidized monosaccharide and one's D-glucosamine, the one we were talking about earlier. And this whole 2 monosaccharide unit is charged. It's negative. And that's part of what gives it that unique property of being an anticoagulant. It just won't let things clot together. Right? So what's the role of heparin? It's an anticoagulant, and it's used to prevent blood clots. So now you know whenever you're on TV and you hear somebody say that that's a blood thinner, you're going to know that they're wrong. You're going to know the right term. It's an anticoagulant. Okay. All right, that is the end. Yep, that is the end of our in-class problems. Yes, you do have a cumulative final exam. Yes, you will, Shelby. Okay, so what I want to do is I want to look at the activities. So let's look at the glycosidic bonds. Oh, I think I wrote all my answers on this one. Where's my glycosidic bonds that I haven't written on yet? Hang on, y'all. I think I'm gonna have to send it to myself again because I want to show the things. All right. So what I want you to do right now is I want you to pull up the one that's glycosidic bonds, and I want you to start trying to answer it, and we're gonna work on it together. But I need to send myself a blank copy of it because apparently I don't have the blank copy on my iPad. So right now, pull up the glycosidic bond activity that was on Moodle that I showed you. So Jade, yes, you can go back to your exams. So they're on Moodle. And so you can go back to your exams and you can see all the questions and you can see everything you got right, everything you got wrong. You can see the feedback on it. It is there for however long you have access to Moodle. Yep. And if you ever have questions, you can always set up a Zoom with me and I can answer them for you. What was the answer for 6.50? 6.50, it's an anticoagulant that's used to prevent blood clots. And Tony, no, it will not be some of the same exact questions. It will be similar, but they will not be the exact questions. Like they'll be the same topics, but they'll be different questions. Okay. Will we have some sort of review? Yeah, I need to look at when we can do that, but sure, I could set up a review. Maybe I could do a joint thing between my 4T and 5T class, and we could pick like an afternoon or an evening or something like that where we can do a review. Yeah, I'll look into doing that. I know it's a lot of material. I know that. I know. Okay. Well, reducing sugars came through, but my glycosidic bond didn't. That's really weird. But y'all should be working on glycosidic bond right now. All right. Eventually we'll get this. All right, so this is what you should be looking at. Is this what everybody's on? This one, the glycosidic bond, activity 22. Yeah, okay, good. All right, so when we're looking at glycosidic bonds, I feel like this was one of those where y'all needed a little bit extra reinforcement on some of this. And so this was just kind of like an extra help for this sort of a couple of these topics. So when we talk about glycosidic bonds, right? When we form them, when we're forming a glycosidic bond, we're having a condensation reaction, right? Because we're going to take a hydroxyl from one of our sugars and we're going to take a hydrogen from another sugar and we're going to make water out of it. And so remember, this is that common format of you have an R group attached to an OH plus another hydroxyl group attached to another R group. In this case, this R group is just our sugar molecule, right? And what happens is you take this OH and you take this hydrogen and you make water out of it, and then you combine the two and you have an oxygen in between. Well, what did we do? We combined 2 sugars and we have an oxygen in between. So it's the same condensation reaction that we learned before. We're just now doing it with sugars, okay? All right, so in figure 1, the glucose molecules that are reacting in the condensation, are they shown as the alpha or the beta anomer? So how do we know if we are alpha or beta anomers? We're gonna look at our carbon 6 up here, the carbon that's outside of the ring. And then we need to look at our anomeric carbon. So here's our anomeric carbon because we're bound to an oxygen here and we're bound to an oxygen. You got a question? Or no? Okay. All right, so we have our oxygen down here. So is the hydroxyl group on the same side of the ring or on opposite sides of the ring as the carbon 6? We're on opposite. So if we're opposite sides, then what do we need to call this? This is another way of saying trans. This is alpha. Okay, so we know if we come over here, this is alpha. All right, and how about our other sugar, because we have to check them both. So this one's on the top side, this one's on the bottom side. So what is this one? Same thing, it is alpha. Good, same thing, it is alpha. So they are both alpha. All right, which carbons are bonded in the glycosidic bond in D-maltose? Okay, so here's our D-maltose, this is our product. We wanna know which carbons are bonded. All right, so what are we looking for in our molecule? Anomeric carbon, you always gotta go to that anomeric carbon, right? All right, so we find our anomeric carbon by looking at oxygen and oxygen. We see we're bound to 2 oxygens, so this one's anomeric. So we're gonna look and we wanna know, is there any other carbon attached to that anomeric carbon? And in this case, no, there's not, so we can start it at number 1. So I could go around and number all the carbons in that molecule, but I don't have to because I'm only trying to number my anomeric carbon. Okay, so now on my other one, here's my anomeric carbon. My anomeric carbon has an oxygen and an oxygen. Now I have to count 1 because there's no other carbon next to it, 2, 3, 4. Now there's my carbon that's interacting in the glycosidic bond. We have 1 anomeric carbon that's participating and then 1 regular carbon that's participating. So our question is, what carbon are they? This is carbon 1 and this one is carbon what? Carbon 1 and carbon 4. So if the CH2OH was bonded to the anomeric carbon, yes, yes, yes. If you had a carbon instead of a hydrogen here, if this were a carbon, CH2OH, then this would be 1 and your anomeric would be 2. Okay, so let me go back. All right, so C1 and C4, yes. Okay, so come down here. We're going to put it in. Carbon linked to the glucose on the left, that was carbon 1. And carbon number linked on the glucose on the right was carbon number 4. So do we know why our glycosidic bond is called an alpha 1,4? Because it's telling you the orientation of the individual monomers, right? We're calling it an alpha 1,4. Why are we calling it alpha? Because of where that oxygen is. Alpha is telling us that we're in a trans orientation. So we have 1 carbon above the ring, 1 carbon below, and then 1 and 4 are telling us that it's carbon 1 with my first carbon molecule, and then it's carbon 4 of my second molecule that actually is participating in that glycosidic bond. Y'all okay on that? I love the yeses and the okays. Anything in there is great, right? So let's see if we can explain it. So do we see why? Yes, why? So because on the first saccharide unit, carbon 1 participates in the glycosidic bond. While C4 of the second saccharide unit participates in the glycosidic bond. Okay, and then the anomeric carbon, the alpha, is because the anomeric carbon, so we'll put alpha because the anomeric carbon carbon's hydroxyl group is in the cis or trans orientation. Trans. Okay. So it's important to be able to explain why we call it that so that you can more easily recognize it when you see it in different molecules. So let's look here, right? If we have a disaccharide, if I find my anomeric carbon, I'm bound to 1, 2 oxygens. If I'm on opposite sides, I'm called alpha, right? Because that's a trans orientation. And then I'm 1 carbon, and then here's another anomeric. 1, 2, 3, 4. So this is our alpha 1,4. Let's try a different one. Let's try D-lactose. Can I go back for a second? Yeah. Which one? What do I need to go back for, Jessica? Go, oh, here. Good. Yeah. Okay, so let's look at another one. Let's try to identify D-lactose. You do it. I'm going to be quiet for a second. You do it. And once you get it, put it in the chat. What they said, yes, good. I see everybody's getting it. All right, so I find my anomeric carbon, right? And I look, it's got 2 oxygens. I got a group here, and this glycosidic bond is in the same orientation. So that's going to be beta. I don't have anything attached to my carbon, so I'm going to call that number 1. Here's my other anomeric. 1, 2, 3, 4. So this is a beta 1, 4. Y'all got this. Y'all got this. All right. Now, why in this one do I have an alpha and a beta? Both anomeric carbons are involved in what? You're 100% right. What are they involved in? In the glycosidic bond, because they all have bonds, but you have to be specific about which one. So you have 1, 2, so you have 2 anomeric carbons participating in glycosidic bond. That's one that's you got to be very careful about. They're not always going to be carbon 1, right? In this ring it is. There's 1, right? There's nothing attached to it. But what happened when you came over here? If this is my anomeric carbon here, why isn't this carbon number 1? Why isn't it an alpha, beta, 1, 1 bond? Because I have another carbon attached to that anomeric carbon. And so this carbon gets the designation of number 1. So my anomeric carbon becomes number 2. So this one would be wrong. Okay. And I think we kind of answered some of this already. So determine the glycosidic bond in D-lactose. We did that. And we explained why. Because in our D-sucrose right here, why do we have the alpha and beta? Because both anomeric carbons participate in the bond. Okay, so label the monosaccharides in sucrose as alpha D-glucose and beta D-fructose. So which one is which? Let me erase some of my stuff over here. So I'll call this number 1 and this number 2. So what is number 1? Alpha D-glucose or beta D-glucose? What's number 1? Number 1 is alpha. So this one is alpha, not beta, alpha D-glucose. So this one is beta D-glucose. And how do we know that? We knew that because we're looking here and here. So these are on opposite sides. So that's alpha. We look here and we look here. These are on the same. And so that's a beta. Okay. All right. So let's see what's next. I don't have to go too fast. Why do the glycosidic bonds in maltose and lactose only contain either alpha or beta? Right? So we said sucrose is alpha and beta because this is an activity just to learn. You don't have to turn this one in, Thomas. This is like our in-class problems. They're going to be super similar to the exam, though. It'll be helpful. All right. So why do the bonds only contain either alpha or beta? Right? We said sucrose has 2 anomeric carbons participating. So how about if we only have alpha or beta? It's because they only have only one anomeric carbon participates. And you're exactly right. Now they have a free anomeric carbon. And that's going to be important later. It's going to be very important later. Okay, so you guys try to name A. You try to name A. Name the glycosidic bond. Oh, and circle the glycosidic bond. So once you get it, go ahead and type in your answer for A. And you don't have to name the sugar, you just need to name the bond. Good, 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 good. You should be getting beta 1,4. That is correct. So beta, because we have, here's our anomeric, right? That's the one that's participating in glycosidic bond. So here's the glycosidic bond right here. This is by definition the glycosidic bond. It's between an anomeric carbon and the oxygen. Okay, so if we compare, these are both up, so they're in the cis orientation, so it's beta. And then 1,4, because this is carbon 1. Here's anomeric, that's carbon 1, 2, 3, 4. So it's a beta 1,4. How about B? Y'all try B. Give everybody a chance to try. Y'all are getting it. Alpha 1,6. So where's our glycosidic bond? Our glycosidic bond is between our anomeric carbon and our oxygen. And so that's going to be right here. So there's my anomeric carbon because I have 1, 2 oxygens bound. This is carbon 1. Here's my other anomeric carbon. 1, 2, 3, 4, 5. Notice that this is a carbon, and then 6 is this one up here. So alpha 1,6. All right. And y'all were supposed to do this in groups and stuff, but we didn't do that. Why isn't the glycosidic bond? Well, because it has to be between an anomeric carbon and an oxygen. So look at this carbon right there. Is that an anomeric carbon? No. So it's not a glycosidic bond. If you had something like this, right? If I kind of erase a bunch of this stuff, right? Here's an anomeric carbon and here's an anomeric carbon. So this is a glycosidic bond and this is a glycosidic bond. And so that's why we have alpha beta. Does that make sense? It's only glycosidic if it's between the, yep, they are, but there's only one glycosidic bond. One of the bonds was already there because you had the oxygen bound to the hydroxyl. Yep. Yeah, I kind of had an inkling that y'all didn't know exactly where the glycosidic bond was, but it's only bonded to the glycosidic, to the anomeric carbon. So it's between anomeric carbon, so glycosidic bond is between anomeric carbon and oxygen. Good? Yeah, all right, good. Good, good, good. All right, so let's go to the next one. Identify each of the reactants as either a condensation or hydrolysis and provide the product. So what kind of process are we doing here? Be careful, be careful. Is water a product? This is hydrolysis. This is hydrolysis. We're not producing water, we're using water, and water is actually going to break apart, right? It's going to break apart. And we're going to give one of these molecules the hydrogen, and we're going to give the other one the hydroxyl. So I'm going to copy and paste. Right, I'm going to copy and paste my image. Will it let me do it? I might have to do it over here. Hang on. Let me do this. All right, there it goes. There's our, that's where our answer is going to be. Okay, so I'm going to break this glycosidic bond, right? And one of those is going to get, whoa, one of those is going to get the oxygen, just one of them. So this is all the atoms that were there. Now I'm going to take my water. My water is really HOH. So whichever molecule didn't get the oxygen is going to get the hydroxyl. So what are we going to do? Give that one the hydroxyl, and then what do we give the other molecule? Just our leftover hydrogen. And so we use the water to break apart this big molecule into two smaller molecules. So this is hydrolysis. Y'all okay on that? Yes, no, maybe so. Okay. Thank y'all. Thank y'all. It's so hard when it's, I don't even get to see you. Oh, do we have to name it? No, we don't have to name it. And provide the product. We don't have to name it. Okay. So how about the next one? We could name it. You should be able to name it, knowing what it was before. If it's maltose, what does maltose turn into? Ooh. If you take maltose and you undergo hydrolysis, what does it turn into? Two molecules of the same thing, D-glucose. Oh, you should, yes, glucose, good, good, good. All right, now we have galactose and we have glucose. What do you think we're gonna make? What kind of a reaction is this gonna be? Not sucrose, lactose. We're gonna make D-lactose. That is correct. Okay, so what's gonna happen is we're gonna go from two monosaccharides to a disaccharide, right? So here's my monosaccharide, and I'm gonna put my other one. Whoop. Okay, so what's gonna change? Anybody have ideas? It is a condensation. When we have condensation, what are we gonna produce? I'm like totally running out of room. We're gonna make water. Okay, so I'm gonna kind of zoom in, maybe, and I'm gonna make water. That's gonna be my other product. So where's that glycosidic, where's that water gonna come from? Well, I need an OH and I need an H, right? So that OH and that H are gonna turn into water. So what we need to do is we need to get rid of them. So I'm gonna get rid of them. So what happens when I get rid of a hydrogen and an OH, right? So that means I still have, gosh, I gotta stop doing that. I still have an oxygen here. I got rid of just a hydrogen. So I still have an oxygen there. What's gonna happen is you're just gonna link the two. Okay, so now, what do we have? A disaccharide. Awesome, right? What do y'all think? Can you predict these products? So all you do is take those individual monomers and pull off a hydrogen from one and pull a hydroxyl from the other and link them where you pulled the hydrogen and the oxygen. But why did I pull from that particular place? What is this? What is this carbon right here? The anomeric carbon. Good, the anomeric carbon. So at least one anomeric carbon has to participate in the reaction. So there are a couple of different ways that you can do it, but That's okay. All right. Circle the glycosidic bond. So where's my glycosidic bond? So all you have to do in this one is circle the glycosidic bond. So I got to go find my anomeric carbon. It's between my anomeric carbon and my oxygen. So if I were to circle it, I would circle right there. Yeah, that's the good thing. That is the good thing, that you don't have to draw on the exam. That is true. All right, so where's my glycosidic bond on the next one? Take a look, see if you can find it. Find your anomeric carbon, and then find the oxygen that's linking it to another molecule, and that would be right there. Okay, so now we're given a new structure. They want us to name the glycosidic bond between monosaccharide A and B. So here's A and here's B. The homework, oh yeah, I know. The homework where you have to design them, I know, but it makes the exams easier. If the homework's harder than the exam, that's a good thing. You don't want it the other way around. Finding and naming. You'll have some like that. Not all, but you'll have some like that. And then like predicting products, you'll have to select the right product. What kind of a reaction is it? Things like that. So how would you name the glycosidic bond? What would you call this glycosidic bond between A and B? Anybody? This is an alpha 1,3. An alpha 1,3. That's kind of a weird one, right? It's hard to know the orientation. Okay, so if you look at molecule A, right, here's my anomeric carbon. I have one oxygen here, and then I have a second oxygen here, right? So I'm going to try and number my carbons. I know I can number my anomeric carbon 1 because I just have a hydrogen attached to it. So that's going to be number 1. And I don't have to go anymore because that's the one participating in the glycosidic bond. Now, look at your next B molecule. Find your anomeric carbon. Here's your anomeric carbon. It's bound to an oxygen, and look at this. It's bound to another oxygen. So you know that's an anomeric carbon. But I can't number this number 1 because I have this CH2OH group right here. So this carbon gets number 1. The anomeric carbon gets to be carbon number 2. Then carbon number 3 is this corner one right here. So this is the one that's participating in the bond with monomer A. I missed the other carbon. Oh yeah. If you miss that carbon right there, that'll get you. So you have it a 1,3. And then how do we know it's alpha? Here's our CH3 at the top. Here's our glycosidic bond, and it's opposite, it's trans, so it's alpha. Okay, so we have a glucose and a fructose inside of our trisaccharide. Which one is glucose and which one is fructose? Any takers? Which one is glucose? What do y'all think? Anybody else? Okay, so glucose A is correct. B is correct for fructose. How about C? What is C? Anybody have any ideas? Good question. It is also glucose. It is also glucose. Why is it in the ring? Because the way it's oriented, they basically flipped it. And so instead of the CH2, CH3 going up, now the CH2, CH3 is going down. But you really won't have to look at ones that are going down. I won't do that to you. I promise. They're all going to be going up. Yeah, I know. It's kind of weird. Okay, So let's go and skip to here. So our reducing sugars. So remember how we were talking about reducing sugars? We were talking about having that free anomeric carbon, right? So let's kind of look at this. This is the Benedict's test. We kind of talked about this in lecture, right? So if you have a positive result on a Benedict's test, it's telling you that you have a reducing sugar present. So glucose, for example, is a reducing sugar. So when we talk about reducing, what does that mean? What does a reducing reaction happen? Like oxidation reduction. Somebody remind me about oxidation reduction. Oil rig. Yes, oil rig is one, right? Oxidation is loss of what? Electrons. Reduction is gain of electrons. What else though? If we're talking about carbon molecules. Oxidation is also gain oxygen and or loss, if I could spell, loss of hydrogen. This is one of those things that you're going to write on your exam scratch paper as soon as you can, right? So then reduction is the opposite. We're going to gain hydrogen and then we're going to lose oxygen. So get your exam scratch paper, show it to the camera that you've got it clean, put it down and write, go to town, write on it. This you should write. Okay, so if you have a reducing sugar that's present, what's happening? So look at the D-glucose molecule. Tell me what's happening to this molecule. So this is D-glucose and this is our product. Is it undergoing oxidation or reduction? It is undergoing oxidation. How do you know? So going from D-glucose to D-glucagonic acid, because it gains an oxygen. This is the oxygen that it gained. Everything else in the structure is exactly the same except for this little part right there. And it formed an alcohol. That's exactly right. Oh my gosh, y'all are on the ball. Awesome. So it gained an oxygen. Y'all are so awesome today. Okay. So copper 2, is it undergoing oxidation or reduction? How do we figure this one out? This is a little more tricky. Cu2 plus has a charge of what? +2. Now, how about this copper over here? What's its charge? Be careful. I know y'all want to say 0. Y'all do. This is an ionic compound. An ionic compound must have an overall charge of 0. So if you combine 2 coppers and 1 oxygen, you're going to have an overall charge of 0. But if you go look on the periodic table and you go look for oxygen, oxygen's in column 16 or 6A. So it wants to gain 2 electrons. So oxygen is going to be a -2. Copper is going to be a +1. How do you figure that out, right? If you're Cu2O, you can take the subscripts and turn them into charges. You just have to remember that on the left is the positive and on the right is the negative. So your metal is always going to be positive. Your non-metal is always going to be negative. So your copper, you went from a +2 to a +1. So what happened for that to occur? Be careful. If I'm a +2, I need to gain 1 negatively charged particle in order to equal to +1. So I'm going to gain an electron. So I gained 1 electron. If I gain an electron, remember oil rig, this is going to be reduction. How y'all doing with that? It's hard to see your faces. No, to not see your faces. I gotta flip my yeah, a little bit. But if you just remember your rules for writing ionic compounds, you're given the formula, right? But how did you get that formula? Well, I had to go to the periodic table and get the charge for oxygen. And I had to actually be told the charge on copper. But if I know oxygen and my compound has to be 0, then I can figure out the other one. So it's just practice going backwards. All right, so remember, if you have a carbohydrate with a free anomeric carbon, so a carbon that is not in a glycosidic bond, this is a reducing sugar. So let's look at some of our examples, right? Find, first of all of the anomeric carbons. This should be really easy, right? So where are the anomeric carbons? So in this first one, what carbon is the anomeric carbon? Tell me like the number. C1. So C1, it's right there. There's our anomeric carbon. Good, good. Let's go and do beta D fructose. Which carbon? Carbon 2. Oh, y'all are dynamite today. All right. Okay. How about here? Tell me on the first, on we'll call this A. Tell me on A, which carbon? So carbon 1, good. How about on molecule B? Still carbon 1, good, 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 good. All right, and how about on our last one? Let's do A and B. Tell me about A. Carbon 1, tell me about B. Carbon 2. Y'all are so active in the chat. I love this. I love this. Y'all are so awesome for being on and doing this. All right, so now that you've identified your anomeric carbons, now you need to know which ones have reducing carbons in them. So look at D-glucose. Is this a reducing sugar, yes or no? Yes. So yes, it's reducing. Okay, so the C1, yes, C1 is reducing, right? Okay, how about on fructose? Reducing or non-reducing? Or I guess you could say yes or no, but reducing, good. I'm sorry, I need to be more consistent. All right, so this one is reducing at carbon 2, all right? How about here? So tell me on molecule on A. Reducing or non-reducing? On A, we are non-reducing. On A, we are non-reducing because A is participating in that glycosidic bond. How about B? This one is reducing at C1, right? Okay, and then how about sucrose? We'll do A. Non. And B. Good, good. Y'all are ahead of the game. Non-reducing. Awesome. Awesome. All right, so it sounds like I think y'all are getting this. I think y'all got this, right? What could you tell me about, could you make a generalized statement about monosaccharides? Anybody? All reducing. All mono are reducing. How do you know if it's reducing? if you have a free anomeric carbon, so reducing, you have a free anomeric carbon. And what is a free anomeric carbon? Carbon, anomeric carbon, not participating in glycosidic bond. Lillian, does that answer your question? Can you identify if an entire disaccharide? You can identify individuals, and then you can also identify as a whole. So like, for example, sucrose over here as a whole is completely non-reducing. So it doesn't matter how many sucrose molecules you would have a solution that is non-reducing. Whereas D-lactose is a reducing disaccharide because it has a free end. Now, when you get up to those chains that are like massively long, you know, they're like 4,000 residues long of glucose molecules, what you'll see is you only have one reducing end and you have all of these sugars, and so they'll basically test negative just because the chain is so long. So if it's non-reducing, no, it just won't participate. It will not participate in an oxidation reduction reaction, Shelby. If it's non-reducing, it will not participate in an oxidation reduction reaction. Y'all have great questions. Great questions. Okay, so, but we already said this. Based on the definition, which of the carbohydrates above are reducing? So what do we say? Glucose is reducing. Which other one? Fructose and lactose. Those are our reducing ones. Can we leave? Yes, you can leave. Yes, because this is the end. I think this was the end. Go. I'm sorry we went a few minutes over. Yes. So those are our reducing. This is the only one that was non-reducing is sucrose. Okay. Yes, I'm going to post this video on YouTube. Yes. Any other questions? That's it. That's all I've got for y'all today. And y'all need to go and I'm going to post some more stuff on Chapter 7 later today. So you'll have all your Chapter 7 stuff later. Okay. If y'all have any questions, let me know, because yeah, I got to start another Zoom in like 10 minutes. Good. I'm so glad it helped. I'm so glad it helped. I thought y'all were kind of struggling a little bit, so I wanted to do this with y'all. Yay. Good. Woohoo. Awesome. All right. And if y'all have anything you need, please, please let me know. Y'all have a great day too. Stay safe, stay dry. You too. Have a great day. Okay, I'm going to go ahead and end this one so that I can start my next class. I will talk to y'all later.